All right, so let's look at some of our data that we got. So if here was the ring, and this is the rope that was perfectly straight down, so to speak, what
whichever rope you feel like is
balanced with a mass of what?
At the 0 degree mark, we had a 50 gram.
50 gram. Okay, so that's not this vector. That is just a value I'm going to put beside it. Okay, and then if this were the horizontal, so to speak, because we have to measure an angle to something, what did we have in the other two directions?
At 143 degrees, we had 30 grams.
143, like right here?
Mm-hmm.
And will you tell me again what that mass was?
30 grams.
All right, and that was, we'll get to the angle in just 1 second. And then the other one?
The other one was at 239 degrees, and the mass was 20.
Okay. Again, these are not the actual weights. These are, or those are not weights. Those are just the mass that was needed on that string. So let's label a couple of these things. Let's see. Let's label this force tension 1. I love some subscripts. And force tension 2 and force tension 3. You can call them A, B, C, X, Y, Z. I don't care. Doesn't matter. All right. So now the angle from 0 was what? 100 and
43.
That was 143. So then what is the acute angle here to the x-axis?
143 minus 90.
Okay, 143 minus 90.
53.
53. So this would be 53 degrees right here. All right, to go all the way from 0 to this third chord was how many degrees? 239. And then this would be from 239 to 270. 270 minus 239. 31. So far, so good? Okay. So now if we start with one of these weights, okay? So what was FT1? What would FT1 be equivalent to?
50 G.
Well, the mass should be in what unit?
0.05.
0.05, and then times the gravitational field constant, which I'm going to use 10 because it's nice to use in class. So what's that? 0.5, and the unit for force is Newton. Okay? And so then, following that same path, FT2 would be what? 0.3 newtons. And then FT3 would be 0.2 newtons. Okay. Any questions so far? All right, so let's just say that we start with these known. So if FT1 is known as being 0.5 newtons, and I'm going to call it theta 2 because it's the angle to the second tension rope is 53 degrees, and theta 3 because it's to the third tension rope would be 31 degrees. Let's calculate what FT2 and FT3 should be ideally. Okay, so then what is FT2 and FT3 ideal? Because you've got a value, right? So either I can use those forces and figure out which angles, or I can use the angles and determine the forces. I think it's a little bit easier to use the angles because we don't have to deal with all the inverse sine stuff as much. And you'll see what I mean in just a minute. Okay, so if we just go back to that original object, and I'll draw it again here. So this tension force here was 0.5. We have one over here that's at, not drawn to scale at all, 53 degrees. And then, again, not drawn to scale at all, 31 degrees, and this is FT3. Now, each one of these forces is doing two things. It is pulling horizontally, and it is pulling vertically. So there's like a vertical component. Remember when we did velocities, and we'd have a velocity at some angle? So this would be our initial velocity, and it would be at some angle theta. Could you find the x component of that velocity? Yeah, it would be like, what, v naught times adjacent, so it would be cosine theta. And could you find the vertical component?
Yes.
Yeah, and that would be the v naught sine theta. Okay. My theta fell off the page. All right. So now, in order to look at the system in equilibrium, it's not just the x direction that's in equilibrium, but it's the y direction that's in equilibrium. And in math class, can you add x's and y's?
Yeah.
If you have a 2x plus 4y, is that 6xy?
No.
No, that's not equal.
Well, but it is 2
So-
times x plus 2y.
Alright, so just like this is a we don't add x's and y's, we don't add x and y direction. You can sum up everything that's happening in the x direction. You can sum up everything that's happening in the y direction. So if you sum all the forces in the x direction and it's balanced, we sum all the forces in the y direction, it should also be balanced. Because what are we studying right now? Equilibrium. Perfect. Okay. So in the x direction, now you can just put your coordinate system wherever you want to put it because you have the ability to set whatever coordinate system you want. I like for this to be my x-axis and this to be my y-axis. Now I know in your math classes you always put little arrows at the end of coordinate graph things to mean that it goes on forever and ever. But if you start putting little arrows on the ends of those things, it looks like extra vectors. So it's just a reference coordinate rather than a math graph coordinate system. So there's a difference. One is just for position reference, one is for graphing. And graphing in math, I get it. Yeah, we're going to go on forever and ever. The axes never end. But this is just a reference dotty dot line. Okay, so in the x direction, so that's this horizontal direction, I like to start and go around the circle, so to speak. So I'm going to start with my force tension 1. Is it in the x direction, y direction, or both? It's only in the y direction. It's only down. It doesn't have a over and up or a over and down or anything like that going on. So it doesn't have any x component at all. Now FT2, so I'm going to go up here to this one right here. FT2. Does it have an x component, y component, or both? Both. Alright, so we want to find the x component here of that force. So just like we used this this trigonometry to determine the base of the triangle and the height of the triangle, I want the base of the triangle I can make with that force vector. So what would that base be equal to? FT2, and then cosine of, I'm going to go ahead and put in the 53 degrees because theta's 1 and 2 or 3 and 4, or x and y just get kind of messy right now. Now, is that vector pointing left or right? And do you want left to be positive or negative? Negative. So we need to insert the negative sign. All right. So I've done force tension 1, I've done force tension 2, now to force tension 3. Does it have an X component?
Yes.
Yeah. And so if I use the same model, that would be ft3 times the cosine of 31 degrees. And I've taken care of all three of the vectors, set it equal to 0. Why did I put plus ft3?
Because the right is positive.
Yes, that X component of ft3 was positive, pulling it to the right and up. Now let's look at the Y direction. Let's start again at the bottom here, and I'm going to go clockwise around. So ft1, X, Y, or both? Y, positive or negative?
Negative.
Okay, and because it's all, the whole vector, is there any sine or cosine component? No way. All right, it would just be a negative ft1. Now what about ft2? Does ft2 have a y component?
Yes.
Yes. And if I were to use that same trig model there, I would have ft2, opposite is sine of 53 degrees. Why did I use the plus sign there? Yeah, it was pointing up. And then the last one, ft3, and we would also have a sine function, because again we're looking for the opposite side to the angle. So I guess instead of Pocahontas today, I'm Sokotoa. You look like you were asleep. Okay, so now I have two equations. And how many unknowns do we have?
2.
Do we know ft1?
Yes.
Yeah, I know ft1, so that's good to go. And so all I can do now is have to do the algebra. The physics part is over. And I know the next bit, the algebra bit, is going to seem like a pain in the butt, but it's less important than getting to the physics part and knowing what you have, okay? That's why it's always important to show your work when you're doing a free response question for me to score. Okay, so ft1 we've already determined was 0.5 newtons from up here. So now let's see. If I rearrange this, ft2 cosine 53 degrees would be equal to ft3 cosine of 31 degrees. So far so good? And could I say that ft2 sine of 53 degrees plus ft3 sine of 31 degrees is equal to ft1, which is 0.5? There's no rhyme or reason. Just because it's on the left side, I'm going to say ft2 is ft3 cos 31 divided by the cosine of 53. So I can cancel the cosines, right?
No.
No! Silly kids.
You're the one who brought it up.
Alright, so ft2. If I make then this substitution over here, so take this whole big nasty, and we're going to dump the whole thing in over here. So then we'll have ft3 times the cosine of 31 degrees divided by the cosine of 53 degrees times, don't forget there was a sine 53 hanging out over here. Most common mistake of all time.
And sine of 53 times 1 over cosine of 53 is tangent to 53.
You can reduce that if you want to. So then ft3, oh, I could pull that out of both sides, right? And have cosine of 31 degrees times the tan of 53 degrees plus the sine of 31 degrees is equal